Hey, Mathmania here. Today we're going to be taking a look at the difference between Rolle's theorem and mean value theorem. Okay, so Rolle's theorem and mean theorem are very similar, but personally I like to go over mean theorem first because Rolle's theorem is just a derivation of mean theorem. So let's actually explain what mean theorem is right now. So on your screen right now we have the coordinate plane x and y, and we see we have a curve denoted in the black color, which is f of x, and we see we have two lines. Now these two lines are going to be really important moving forward. But first, let's point out the obvious. In order for the mean value theorem to apply, so for the mean value theorem to apply, you need to, I have no idea how to spell theorem, let's just say mean value. In order to apply the mean value theorem, you need to be sure of two things. You need to be sure that your function, f of x, is continuous over the domain you're taking, and this domain is going to be inclusive. So it has to be continuous over its domain a to b, and let's just say that the coordinates of a is a comma f of a, and coordinates of b is b comma f of b. So is this curve continuous on the domain a comma b inclusive? Yes it is. There's no asymptotes, there's no holes, it's continuous. So that checks off this box. Now comes the second condition that we need to take care of before applying the mean value theorem. The second condition is very similar to the first condition, except the second condition says f of x is differentiable over the open interval a to b. And looking at this, can we say that it's differentiable? Differentiable just means that at every single point of the graph, can you take a derivative, or is there a tangent line for every single point in the graph? And yeah, I mean, if you take any point on the graph, we see that's a tangent line. If you take this point on the graph, we see that was horrible. If we take this point on the graph, we say this is a tangent line. No matter what, there is one unique tangent line for each point on this graph. And these are the two conditions that must be met before applying the mean value theorem. Now, this is just scratching the surface. What really is the mean value theorem is that if your function is continuous and differentiable over its domain a to b, then we say that the slope of the line connecting point A and point B, which is y2 minus y1 over x2 minus x1. Now let's actually put it in the form of these coordinates right here. That is going to be, let's say y2 is f of b. That makes y1 f of a. And then x2 is b, x1 is a. Now that is the slope of this line. And the mean value theorem says if your function is continuous and differentiable over the domain a to b, then there exists a point on the curve f of x such that the tangent there is parallel to the chord joining the ends of the curve. Now, what did I just say? That's basically saying that there must be a value c in between a and b, so in between the domain, that when you draw a tangent to that x value, the slope of that tangent will be equal to the slope of the line passing through a and b. And we can see that right here. The slope of the line passing through point AB is the same as the tangent slope of a line at x equals c. So to write this numerically, we can say that f of b minus f of a over b minus a, that will be equal to the slope at a point. And let's say that point is x equals c. So we're saying that there must exist an x value c, that when you draw a tangent to that x value, then the slope of that tangent line will be equal to the slope of the chord passing through a comma b. That is basically what the mean value theorem is talking about. So now let's move on to the Rolle's theorem. The Rolle's theorem is really similar to the mean value theorem, except with a few minor differences. So your first two conditions are still going to be the same. Your function, in this case we have g of x as our function. Your function still has to be continuous. So g of x is continuous. And the second one is also going to stay the same. G of x also has to be differentiable. And, going back to the first one, it has to be continuous on the inclusive domain a to b. And then the second one is g of x is also differentiable on the open interval a to b. And now there's also a third pre-criteria, essentially, that needs to be fulfilled before you can actually apply Rolle's theorem. And that is g of a has to be equal to g of b. And we see that is true in this case because we see that the y-coordinates are the same on the graph to your left. And those are the three conditions that must be met before you actually apply Rolle's theorem. Now, what does Rolle's theorem actually state? Well, Rolle's theorem states that if all these three conditions are met, then there exists at least one point, let's say that point is c, comma, g of c, lying between a and b, so it lies between the domain, where its slope is tangent to the x-axis. Now let me rephrase that again. So we have our domain a to b, and now Rolle's theorem says that there must exist a c between a and b, that if you draw a tangent at x equals c, the slope of that tangent is going to be 0. Hence, it's parallel to the x-axis. And we can see that right here. So in this scenario, g of x is a parabola, but honestly, it could be anything. So in this case, we see that this is going to be x equals c. So this point is essentially c comma f of c. And we see that at x equals c, we drew a tangent, and that tangent has a slope of, so I'm going to say it has a slope of 0. And when a line has a slope of 0, it means it's parallel to the x-axis. So therefore, Rolle's theorem just says that in between a and b, if the y values are equal, there must exist a c that when you draw a tangent at x equals c, that will be 0, or parallel to the x-axis. Alright, so this is our first question. We're going to be dealing with the mean value theorem, and in a lot of the questions you're going to see mean value theorem abbreviated as MVT. So just know that you're going to be dealing with the mean value theorem. Now let's just dive into the question. Find point C on the indicated interval using MVT. F of x is equal to x times x minus 2 on 1, 3 inclusive. So our first two things we need to check is if this function is continuous and if it's differentiable. So let's check that. Let's see, is f of x continuous? Is it continuous? And in this case, f of x is a polynomial because if you expand f of x, you get f of x is equal to x squared minus 2x. And we should know that all polynomials are continuous over their domain. So that fixes, or that checks off this box right over here. It is continuous. Now let's check if it's differentiable. So let's check if it's differentiable. Differentiable. Now, this is kind of similar to continuity, but I think seeing if a function is differentiable is a little bit trickier. But in this case, let's just imagine it in our heads. We know that this is what? A parabola, right? We know this is a parabola, so it's going to look like that. So from this parabola, we could see that no matter where our point is, we can always draw a tangent to it, no matter what the domain is. So if we just shrink that domain to 1, 3, it should still be differentiable. So that checks off this box. There are no holes, there are no cusps, there are no corners, there are no asymptotes. It's differentiable. So in this case, it is continuous and differentiable. And MVT states that the line passing through point A and point B at the endpoints, the slope of that line is equal to the slope of a line tangent to x equals c. and we're supposed to find that c value. So if you remember the MVT formula, that was f of b minus f of a over b minus a is equal to f prime of c. And I want to note that we're supposed to find c. So what is c? And actually, scratch that. We're supposed to find c, but also we're supposed to find f of c because it's asking the point. So we're going to find c, f of c. That is what we need to find. So in this case, we know our a, we know our b. We can also find f of b and f of a. How do we do that? Well, let's see over here. Let's assume b is 3. So let's assume b is equal to 3. Let's write that here. Assume b is equal to 3 and a is equal to 1. I'm using these values because a and b are the endpoints as we saw from the graph earlier. So now we have f of 3 minus f of 1 over 3 minus 1, which is just 2. And now let's just focus on the left side. Let's try to figure this out. F of 3, we could find that out. Let's just plug it into this function. So we have 3 times 3 minus 2 minus, we can also find f of 1, plug it back into that same function. We have 1 minus 2 over 2. Simplifying this, we get 3 times 1, which is just 3. We get minus 1 times negative 1, so that's positive. Over 2, we get 4 over 2, which is equal to 2. So the slope of the line connecting the endpoints is 2. Now we need to find the point where we can draw a tangent, and that tangent slope is also equal to 2. So in this case, we have to take a derivative. We have to take the derivative of f of x because that will give us the slope at each and every single point on the graph. And then we could just set that slope equal to 2 and find the x value pretty easy. So let us find f prime of x. This is a simple polynomial. We are going to differentiate x squared minus 2x, so that is just 2x minus 2. We're going to set this equal to 2 because that is exactly what our formula states over here. We found LHS is equal to 2, and we have to find f prime of c, which is also equal to 2. F prime of c in this case is going to be 2 because the slopes have to be equal. So in this case, we could say f prime of c, 2c minus 2 is equal to 2. Now it's just a matter of finding c. So we have 2c is equal to 4, c is equal to 2. Now that's the x value. We still have to find the y value. And that's pretty easy. We would just replace it into that formula again. So we have f of c, or f of 2, is equal to 2 times 2 minus 2, which is 0. So the y value is 0. So now our answer is 2, 0. All right, so let's do one more problem using MVT, and then we'll get on with the Rolle's theorems problems. So in this case, we have pretty much the same problem except different function and different endpoints. So if you want, feel free to pause this video and give this problem a go. But right now, I'm just going to go over the solution. So once again, we're dealing with MVT, and we have to find the point. So we're finding c, f of c. That's what we're trying to find. And let us bring back our MVT formula. That is f of b minus f of a over b minus a is equal to f prime of c. But before we apply MVT, we need to check if this function, f of x, is continuous and differentiable. So let's see that. Let's see if it's continuous over the domain 2 to 4. So is f of x continuous? And in this case, f of x would be continuous. How do I know this? This is because if I replace 2 in f of x, so if I replace 2 in f of x, I get square root of 4 minus 4, which is 0. So that's a valid point right there. And if I find f of 4, I get square root 16 minus 4. That's square root 12. We could simplify square root 12. That's 2 square root 3. And in this case, this graph would look a little something like that. Oh, not like that. Little something like this. So this would be 2. And in this case, we're dealing with this domain right over here. And in this domain, we see that, hey, the graph is continuous over this domain, because this is usually how a square root function looks. So we're saying, okay, between 2 and 4, the graph is continuous. So there we go. The graph is continuous. Let's see if it's differentiable. Well, just looking at this graph, we see that, hey, it is differentiable. You can take a point, draw a tangent. Any point, you will get one unique tangent. So f of x is also differentiable over its domain. And what I want to point out is that I'm saying it's differentiable and continuous over the domain they gave me. I know it's not differentiable and continuous over here. Like if they gave me the domain -1 to 0, these two wouldn't even apply. The function doesn't exist to the left of 2. But in this case, they gave me a domain where this function is continuous and where it's differentiable. So I'm just going to follow that domain. I don't really care if there's an asymptote outside that domain, if there's a corner to the left of that domain. I just care if it's continuous and differentiable in that domain. And in this case, it is. Just wanted to clear that out. We're only looking for continuity and differentiability in this domain. So now we have, it's continuous, it's differentiable. Now let's actually get to the mean value theorem. In this case, we could say f of b minus f of a over b minus a. F of b, let's say f of b is 4, I'm taking the rightmost endpoint, minus f of 2, 4 minus 2, and that's equal to f prime of c. Our goal is to find c. Now we know f of 4, we just found that over here, lucky for us. 2 square root 3 minus 0 over 4 minus 2. And I'm just going to solve the left side for now. So solving the left side, I get 2 square root 3 over 2 equals square root 3. Now, what this is saying visually, this is saying that the line connecting this point and this point, the slope of this is square root 3. Now, I need to find a point on this curve where the tangent is also square root 3. And we know we could find the slope of a tangent by just taking the derivative of the original function. So let's actually do that. So we have f prime of x. Oh, actually, let's do f of x is equal to x squared minus 4. And this is to the power 1/2. And now we can start to take the derivative. Once again, simple derivative, you need to apply the chain rule, but nothing too difficult, hopefully. So we have 1 over 2 square root x squared minus 4 times 2x for that chain rule. 2 and 2 cancel, we're left with x over square root x squared minus 4. But we want to see when this slope is equal to square root 3. So I'm just going to set that equal to square root 3. Now I'm going to scroll a little bit down. So let us solve this part right over here. Let's try to find c, or in this case, x. So in this case, actually, let me just replace x with c to make it a bit more simpler. So replacing x with c, because we don't know what c is, we're going to replace it in there. We're going to have c over square root c squared minus 4 is equal to root 3. And let me move this to this side. So we're running out of space here, but now we have, let's actually square both sides. So we have c squared over c squared minus 4 equals 3. We have c squared equals 3c squared minus 12. I just took the denominator to the other side. We have 2c squared equals 12. Yes, 2c squared equals 12. C squared is equal to 6. C is equal to plus minus root 6. Now, before you start saying that's your answer, always remember, is this c in that domain? So we got two values of c. We got negative root 6 and we got root 6. Let's see if negative root 6 is in that domain. So we have domain 2 to 4 is negative root 6 in that domain. It's not in that domain. So negative root 6 can't be the answer. Now let's see, is positive root 6 in that domain? Positive root 6, that is 2.4 something. And yeah, that looks like it's in the domain. So our final answer will be root 6 for the x value. And now f of c, if we calculate that, we get root 6 squared. We get root 6 squared, which is 6. 6 minus 4 is 2, so we get square root 2. And that is your point. Okay, now let's dive into Rolle's theorem. So here is another practice problem for Rolle's theorem. Verify Rolle's theorem for the function this. And in this case, we're not only going to verify, we're actually going to find that c value. So let me just add it here. Find c value. For f of x equals x squared minus 5x plus 6 on this domain, inclusive. So that is 2 to 3. Feel free to pause this problem and give this problem a try. So now I'm going to go over the solution. So once again, we have those two conditions that need to be met, plus a third condition. So let's actually meet those two conditions first. So is f of x continuous? And in this case, we know that all polynomial equations are continuous over their entire domain, negative infinity to infinity. So of course, it's also going to be continuous over this domain. So continuity is not a problem. Let's check differentiability. I think I added too many i's there, but that's okay. Let's check differentiability. Differentiability in this case is also going to be differentiable. Every single point on this parabola is going to have a unique tangent at this domain. And if you want, you could also graph that, but for now, I really want to get into the Rolle's theorem part. So our third condition, do you remember it? If you don't remember it, that's okay. Just rewind a little, and then that's where I went over Rolle's theorem. But the second condition is that f of a has to be equal to f of b. In other words, the y values of the endpoints need to be equal to each other. So let's see. Is f of 2 equal to f of 3? Let's check that. So f of 2, let's find that. F of 2 is equal to, I'm going to replace it in here. So we have 4 minus 10 plus 6. That's 0. We have f of 3, which is 9 minus 15 plus 6, which is also 0. So yeah, f of 2 is indeed equal to f of 3. Now that we have all three checkboxes checked, that means we can apply Rolle's theorem and find that c value. So let's get into it. So Rolle's theorem, we actually need to find when the derivative is equal to 0. Or in other words, when the slope is equal to 0. So let's actually find the derivative of that. In these cases, if you don't know what to do, chances are 99% of the time, just take a derivative first. So we have f prime of x is equal to 2x minus 5. And that's the slope of every single point on the curve. But we want the point where we draw a tangent. That tangent is going to be 0. The slope of that tangent is going to be 0. So I'm going to assign it equal to 0. And let's find the value of x. Or in this case, this x value will be our c value. So we have 2x is equal to 5. X is equal to 5 over 2. Okay, x is equal to 5 over 2. This is where the tangent of the graph is going to be just a straight line. Its slope is going to be 0. And that's exactly what Rolle's theorem states. And in this case, we also have to check if this x value or if this c value actually lies within the domain. So 5 halves is equal to 2.5, and 2.5 lies in the domain of 2 to 3. So in this case, c is equal to 2.5. All right, so on to our last problem. Verify Rolle's theorem for this function. F of x is equal to x times x plus 3 e to the power minus x over 2 on this interval. Once again, we are going to see those three checkboxes we need to first verify before actually applying Rolle's theorem, and those are continuity, differentiability, and y values being the same. So let's actually get right into it. We have is f of x continuous? And how I like to think about this is that I know this part is a polynomial. I know all polynomials are continuous. This part is an exponential function. I know all exponential functions are continuous. And the thing is, this is actually a law, a theorem. If you multiply two continuous functions, the resulting function is always going to be continuous. And that's also the same with differentiability. So in this case, since both of these continuous functions are being multiplied, the resulting function, which is this whole thing, is also going to be continuous. So that proved continuity. Let's check differentiability. So differentiability. Okay. And in this case, it's going to be the same case as continuous. I know polynomials are differentiable over their entire domain. This one in particular, because no holes, no asymptotes, no corners, no nothing. It's differentiable. Exponential functions are also differentiable over their entire domain. And as a result, if you multiply two differentiable functions, the resulting function will also be differentiable. And our resulting function is this function right here. So that's differentiable. Now our last item on the list to check off is if f of -3 is equal to f of 0. And let's do that right now. So f of -3, excuse me, f of -3 is -3 times -3 plus 3, and I don't even need to go over there. I just know that this is 0 because -3 plus 3 is 0. Next we have f of 0. Once again, it's just going to be 0, 0 plus 3. Don't even need to know what's next. It's just going to be 0. So once again, f of 3 is equal to f of 0. The y values of the endpoints are equal. Now that we know they're equal, we can apply Rolle's theorem. Now in this case, we know that the slope needs to be equal to 0. Let's simplify this function to make it easier. So we have x squared plus 3x times e to the power minus x over 2. In this case, we need to apply both chain rule and the product rule. So let's get started on that. I'm going to make some space towards this side because this can get a little long. So first, I'm going to take the derivative of that. So 2x plus 3 e to the power minus x over 2 plus x squared minus 3x e to the power minus x over 2, chain rule, -1 over 2. Simplifying this, we get 2x plus 3 e to the power minus x over 2 minus x squared plus 3. Let's actually take the x out, my bad. So we're left with x plus 3 e to the power minus x over 2 over 2. And now we want to set this equal to 0. Well, we just need to simplify this a little bit more. So let's actually take the whole thing in a common denominator. So we have 2x plus 3 e to the power minus x over 2 minus x plus 3 e to the power minus x over 2 all over 2. That's equal to 0. We're trying to find the x value because that x value is going to be the c value. Now, in this case, let us take out this e to the power minus x over 2. So my e to the power minus x over 2, we're left with this part, and I'm just going to expand that. So we have 4x plus 6 minus this part. Once again, I'm just going to expand that. That is minus x squared minus 3x equals 0. I just moved the 2 to that side. Now, in this case, let us simplify whatever's in those brackets. So we have e to the power minus x over 2 minus x squared plus x plus 6. Let's take out that minus e to the power minus x over 2. X squared minus x minus 6 equals 0. This can either be 0 when this is 0 or this is 0. But one thing to note, that this can never be 0 because we know that anything to the power of anything, it's never going to be equal to 0. If we have e to the power of 0, that's going to be equal to 1. E to the power of anything is never going to be 0. So in this case, we can also simplify this further. We could say that this is equal to minus e to the power minus x over 2. Simplifying this, we get x minus 3, x plus 2. At this point, it's just basic algebra. We already did the calculus like above over here. Equal to 0. Therefore, x is equal to negative 2 and 3. But once again, we need to check what lies in the domain. Does x equal negative 2 lie in this domain? Yeah, it does. Does x equal 3 lie in this domain? No, it doesn't. So x equals 3 is an extraneous solution. So in this case, c has to be equal to negative 2.